Good morning, everyone, and welcome to my talk. I'm Thomas Sermpinis, and today we will talk about some horror stories from the automotive industry that I hope to amuse you and scare you a bit regarding my experience in the automotive industry that I worked the last 5 years. I'm Thomas Sermpinis. You might also know me as Crow Tom. I'm an automotive penetration lead by day for Auxilium Cybersecurity and the security researcher by night. I like to hack everything. I'm a Trooper speaker from last year's and a Troopers attendee. And if you like to know more boring stuff, you can go to my website. The main goals of this talk, which I want to achieve, are analyze the current state of cybersecurity in the automotive industry, present some unique and hopefully interesting use cases, result of around 100 pen tests and research projects in this industry, educate and endorse more people to join this industry, but also supply interesting insights for the old and bold people of the industry, highlight the significance of these safety-critical components that OEMs brought online the past decade. All these points should supply an understanding of how we approach automotive penetration testing and how it can be extremely different from automotive security research due to scoping, financial constraints, and other limitations enforced by this industry. And let's start, as promised, with an overview of the state of cybersecurity in the automotive industry, discuss where we are, what is planned ahead of us, and where we're currently going. And there are several incidents throughout these years. And there is a really interesting talk from last year from Troopers by Martin about the past 10 years of automotive vulnerabilities, but I still get fascinated by the quality of findings that the automotive industry still has in 2023. Some examples, only from the last year, are some fixed code vulnerabilities in Nissan, which is one of the main examples of this vulnerability in the wild, stealing Kias with a USB cable. I mean, okay, like what the heck? Key fob vulnerabilities again and again and again. Remote unlocks of whole vehicle fleets due to flaws in Sirius XM, which is a head unit operating system that progressively implemented more and more vehicle functionality. Unlocking and stealing vehicles due to easily accessible CAN buses and really bad internal architecture, something that we will also go through later in this talk. And that's only a sample of a huge list of similar incidents in this sector. This is an example for you to understand the state of cybersecurity and why cybersecurity gets so important into the automotive sector. This is the new BMW i7, you might know it. And alongside the common things we usually see in a car, like a head unit, like a heads-up display and everything, it literally contains my whole living room inside. All these services are exposed to the telematics unit, and while vehicles live in isolated networks, one compromised vehicle can act as a starting point for mass exploitation of vulnerabilities that until now could only affect your living room, but now they can potentially extend to the safety-critical computer on wheels that you have. Yeah, sorry, I'm losing my, yeah. So the state of cybersecurity right now, I don't really want to bore you with regulations, but the significant part of it is the current regulation that gets into effect from 2024, which is the UNR 155, and states the requirements for vehicle cybersecurity and provides a set of standards which must be met in order to ensure the safety of road vehicles. The main point of this regulation is monitoring through a certified cybersecurity management system and several other set of standards which are required in order to ensure the safety of road vehicles. To summarize, I would say that it's an effort to shape the completely unregulated mess that exists until now. And the biggest caveat is that penetration testing is solely based on the risk assessment that has been done before the penetration testing. And going through our first part, I want to have a discussion about the Tier 1 suppliers, which of course play a huge role in the automotive industry, with cars being literally Legos, ECUs coming from all sorts of places, and OEMs trying to combine those in secure way from development to production. To start with, we need to talk about cybersecurity requirements, which is, in case of automotive suppliers, it's a document generated in our case by the OEM, specifying the engineering requirements for cybersecurity risk management throughout the vehicle lifecycle. It includes processes, policies, and standards to comply with the legal framework, and preferably protect the vehicle from cybersecurity attacks. In an ideal world, the Tier 1 should comply with those requirements for correct and secure functionality of the supplied components. If those requirements are followed, though, it's a different discussion, and let's go through some real-life examples to lead the complete compromise of the vehicle in a most dumb way possible in this case. To do this, we will understand that several Tier 1 suppliers are based in countries with low transparency and weak governance. And additionally, most of the requirements we see are solely written in a way that the Tier 1s can exploit it by searching for parts that can be hidden between the lines. And finally, not only the OEM, but the dependent suppliers too usually have a reactive approach on security testing, which assumes that everything described on those requirements are followed, which leads to shaping weak penetration testing methodology and test cases with high probability of losing important parts of the attack surface. Of course, we cannot blame some of the two, as financial restrictions and scoping is in the game. To start with our first use case and the path to game over, we need to understand a bit what is UDS inside an ECU and why it's used in most cases. Last year, I spent something like 5 or 6 slides explaining this, so I will do the explain like I'm 5 version now. It's basically, it allows diagnostic functions such as reading, erasing faults, giving authorized access to the client, and many other functions in order to perform diagnostics on a vehicle or on a single ECU. It consists of several services which can be used to perform those actions. And the really common one for authentication is the UDS Security Access Service, or 0x27, and allows elevated access to authenticated users. A really good example that we have here is that we have a client and an ECU. A client and an ECU. Basically, the client requests a seed from an ECU. The ECU generates a random seed and calculates the key with the secret algorithm and the secret key. Then sends the random seed to the client, where the client needs to have access to this secret algorithm and secret key. It sends the calculated key, and the ECU performs this verification between the two calculated keys. And then, eventually, if the calculation is correct, it grants access to the client. What we saw during the years, and regarding this service, there is sloppy authentication implementations many times, where we saw byte additions and single-digit integer additions to the seeds, and other disturbing for 2023 methods of implementing security access. Also discussed last year, most of the times we see weak seed randomness sources, which can lead to complete compromise of most vehicles. One of these is the system clock, as an example, which is really common in the automotive industry. And finally, backdoors implemented outside of the scope of the requirements. As an example, an extra security access sub-service with extremely weak security. And here is a real-world example from one of our pen tests. In this real-world example, we have a target vehicle which we got informed by the cybersecurity requirements that it should include 2 different authentication levels on the application layer. In this case, the security access service should have 2 different sub-functions, which is the number 1 and the number 3. But as we see here, on the seed request, we discovered eventually that there is a 3rd security access implementation, which is the 70. When requesting the seed from the client, in this case, we received the seed with successful seed response, which by itself is weak because it's only 4 bytes. And we can for sure argue on that, on how easily it can be cracked. But in this case, entropy is not an issue. The issue really is that by supplying, here the ECU sends the random seed, but by supplying only zeros, we managed to get a positive response, which is this 6773, and grant access, authorized access to the ECU by just supplying zeros. And that was one of the easiest and first things that we tried. And it's not actually, it's not actually something secure. It's not actually something that potentially the OEM was targeting to implement, but mainly it's from the tier one. And some of the things, like there's several reasons that this might happen, and some of our best guesses, because the discussions between the OEM and us, it's not completely honest, let's say. First of all, it might be that that OEM doesn't know, or doesn't want us to know in this case, or that the tier one did not want to inform the OEM, and this is like an extreme situation that we see some of the times, and if the OEM is honest, then we might have an issue, because these backdoors can lead to complete compromise of the vehicle without the OEM knowing, and then it can lead to several other issues on the streets that we will see later. What can be the solution from our perspective? I can only give suggestions. First of all, for the OEMs, build stricter cybersecurity requirements, as we discussed previously. And for the pen test suppliers or researchers, I would like to suggest that to build a robust methodology, which will cover a realistic amount of test cases for the target scope and the target financial incentives. Don't build it solely based on the requirements. That's wrong, as we saw, because building it on top of the requirements will mean that we are only testing the things that we know they are there, and educate the client in the end. OEM, Tier 1, or anyone applicable in this case, we need to educate them in a way that it will help us secure the vehicle in a meaningful way. Moving forward, we need to talk about the main bridge of connectivity in vehicles of the real world, which is the telematics unit, and how many vehicles get connected, how the vehicles get connected to the network that they should not actually be. The reality is that you cannot actually currently buy a vehicle without a telematics unit, without being connected to some kind of cellular network. There is the necessity of secure updates, which is also required by the regulation that we discussed, RN 155, and monitoring, which should be done in a correct way, most of the times handled by the cellular connectivity that we are looking here. While connectivity, connecting this unit to the internet might sound easy, and it is easy, the fact that it exposes everything that was exposed before on the head unit, for example, to a way wider network is the sad reality. And long story short, we have to consider the applicable connectivity when designing automotive architecture. So now that we have the first taste of how things are getting connected, let's dive into this real-world scenario, which is a supercar manufacturer, actually, that pushed the connectivity of their pre-production vehicles in order to perform secure updates and remote management of the fleet for personalized supports of their clients. These are vehicles that need actually personalized support. In this case, as a first part, we have the telematics unit handling the cellular connectivity and the connection to the internet. And this telematics unit is connected to the main head unit over some kind of interface. This can be, as an example, a serial, Automotive Ethernet, RS485, or anything else that is applicable to the automotive sector and can give some high bandwidth. At this point, one ECU is already connected, and considering that this kind of ECU usually come with several publicly available interfaces, and I'm talking about the head unit, in many cases it also includes SSH or other publicly accessible and publicly vulnerable services, you can understand that this kind of risk is not implemented properly. But there are proper implementations, and limiting the exposure at a minimum using hypervisors to isolate, for example, the exposed system from the rest of the ECUs in the vehicle, and connecting the vehicle and gateways that filter all requests coming from the exposed unit are some of the solutions that usually exist on those vehicles. But this is not usually the reality. And what we can see here is a complete, hypothetical in this case, architecture of this vehicle, where the different domains of it can be seen with the lines connecting to these different boxes. And the interconnection between them, of course. But there is a problem, as you see. As we can see, there are several components which are connected directly to the head unit. And instead of passing through the gateway for proper routing and filtering of the target message. And we find this as an issue. I don't know if you find it too, but interconnected buses can act as a stepping stone to the safety critical components. And you saw that there were several safety critical components connected to these red buses because it was connected through the head unit. Gateways are commonly used, as we said, for message filtering and routing, and by passing the gateway, as we saw on the previous diagram, results in direct interception and communication of CAN messages. At this point, the target ECU existing on those buses can be analyzed, enumerated, exploited without the assumed restrictions. And I don't know if you remember UDS, but we have another service, which is ECU reset. And 90% of the target ECUs that we test come with no authentication or precondition for hard ECU resets. And this hard ECU resets is basically a power cycle. We just turn completely off the unit and we supply it with power again. This means that the ECU, which allows the execution of this service, can be immediately interrupted by hard resetting it. What is the outcome in our favorite EV supercar? Maybe running in like 300 kilometers. As we see here, there are several ECUs that are connected directly. Sorry. Yeah, we have an NDA, so I cannot show you the exact video, but I will show you another one, which is basically a rental car, and you can see that with the same attack, I can actually restart the ECU, which is for the blind spot protection. And you can imagine this in many ways. All the ECUs are interconnected in this case, and as we saw on the previous diagram, I will just jump a bit behind here. We have the BMS, the inverter, and batteries connected. So imagine resetting these units. In this case, the problem would be only that we can either confuse the driver or create some kind of disturbance in the adaptive cruise control if it relies on the blind spot protection. But it's still an issue, and the manufacturers don't always look at it like this. To conclude with this use case, while it was a simple example, we were able to see how bad architecture can lead to devastating results. More internal buses need to be introduced for proper segmentation of safety critical and non-critical components, why not? And better design should be considered from the first steps of production, because then it's really hard to implement it. You cannot actually change the architecture once you start building the actual vehicle. That's almost impossible. Moving forward, we need to have a talk about design choices. We already briefly mentioned some of the pitfalls that the industry fell because of bad design choices, but let me also give you some juicy insights that you will hopefully appreciate. Understandably, vehicle development is way more complicated than simply designing and architecting the vehicle network, with several decisions that need to be made under highly constrained environment, but considering budget and time. One of those issues that need to be resolved is the physical space of the components that get into the vehicle. Where will these components be placed? How will they fit? Are they light enough? And other questions need to be answered in order to create an efficient and working vehicle which doesn't spend 30 liters or have an efficiency of 50 kilometers per charge. On that point, manufacturers need to make sure that everything is secure, isolated, and inaccessible to external users. But what happens if it's not? Basically, this happens. This is the example that we went through in the start of the talk. It's the recent Toyota hack, which proved that this can have devastating results. Basically, attackers were able to unlock and start the vehicle and basically steal it because actually the headlight of the vehicle, behind the headlight of the vehicle, you could actually get direct access to the internal buses of the car. What we usually see on our pen test is that many other components are directly connected to internal buses, and this is due to bad design. And usually these components, these ECUs, are radars, LiDARs, lights, and other things that need to be on the exterior and have access to the exterior of the vehicle. But design choices, as you understand, with bad architecture is not a good combination, and external access to internal buses is a really common misconfiguration that we see on the wild. Taking as an example our previous diagram, we can see that there are several cameras and radars in one of the buses of the ECU. This would not be an issue considering that the bus is isolated from other buses, but because on the same domain we have the electronic braking system, it means that it needs to have access to the braking and steering ECU. But as you see, it's directly connected to the gateway in this case. Considering that all the previous use cases are applicable, we can see the scenario where, due to bad design, an attacker manages to get internal bus access through the front radar. Due to bad architecture, he can access the braking system, and by issuing an ECU reset to the electronic braking system, trigger the emergency braking of the vehicle with potentially devastating results if applied in a highway, for example. Now let's watch a cute video from a truck manufacturer, which will give us some insights in the current topic. I want you to see and understand what the battery isolator is.
As with everything with computers on board, before we call action service out, it's always worth just isolating the vehicle, counting to 10 and let everything reset itself, re-energize the truck and see if that's corrected your fault.
There is no affiliation. So here we have a battery isolator, which is included for several reasons in electric vehicles, in fuel cell vehicles, and other vehicles which require isolation of batteries for safety concerning incidents, isolation of inverters and converters, hard reset of ECUs, and clearance of faults, as he said. What this isolator does, basically, like the name implies, it separates direct current into the underlying components, and it was actually encountered a couple of times during our pen tests and outside in the wild, mainly on buses, trucks, boats, and kind of heavy-duty vehicles. The main question is, should they be accessible in unauthenticated manner, like we saw in the Volvo video? Like, should I be able to go to the vehicle and access these switches? And I will bring it back, don't worry. But for now, let's make a jump to the favorite topic for the automotive in this conference. Later today, Niels and Enrico will have some hardcore glitching attacks to bypass restricted bootloaders. Please join them. But here, we will see other misconfigurations which require almost zero effort to bypass. And there are some easy ways to check that should always be performed during a penetration testing of a vehicle or an ECU. So bootloaders in the automotive are usually architecture specific, but it can be accessed through the application layer protocols, which is common alongside different architectures. ECU bootloaders are usually used for reprogramming, initialization of the application sections of the memory, read and write from and to sensitive parts of the memory. And understandably, security measures must be taken to restrict unauthenticated access to the bootloader. The hard truth is that most of the manufacturers do not restrict access to this part of the memory, which, as you understand, can supply access to some critical functionality. And usually, even if we get access to the bootloader, some of the sensitive services are restricted to authenticated users. And most of the times, these services are the ones responsible for secure update of the unit, as an example, request, download, upload, transfer data, and other services like this. But something that worth to be mentioned is that authentication mechanism, while on bootloader, is completely different from the one accessible on the application layer. And because of this, we concluded in some really interesting observation that we will see now. In this diagram, we see a really simple representation of the application and bootloader parts of the system. The normal boot process starts from the bootloader and then ends up on the application part, where our implemented applications live and manage the tasks which the ECU is programmed to perform. So, for example, when you need to brake the vehicle, this happens on the application layer of this ECU. In some cases, though, we can use an application layer protocol that we discussed earlier, UDS, and issue a session change to the programming session for reprogramming an ECU, which will technically redirect us to the bootloader of the system. And as you understand, many manufacturers leave this unauthenticated, so access to the bootloader can be obtained with the excuse that the services under the bootloader are authenticated in this case. Yeah. Basically, I lost something. No. So, in our experience, this UDS diagnostic session control for programming session is most of the times accessible to unauthenticated users. But what happens if it's not? How do we proceed if we cannot access it directly by switching our session? And you need to remember the ECU reset. We technically perform a complete power cycle of the unit. So this means that we have to go through the boot process again to obtain access to the application space. So go through the bootloader and switch to the application layer eventually. But what if we manage to stop the boot process at the stage in which we are actually accessing the bootloader section of the memory? To do that, we can start issuing a tester present service. It's another service which says to the ECU to stay at the current active session and not move to the default one, used to help clients to avoid repeated sending of diagnostic session requests. So technically, as the boot process includes access to the bootloader and programming session of the unit, by issuing a tester present on the appropriate time window, we can technically stay at the session and access the bootloader part. And as you understand, we can repeatedly send the tester present before and while booting to have higher chances of success without leaving a gap between these requests. But what if even ECU reset is restricted and we cannot access it? So this use case, I can say that it's mostly applicable to a test bench, that we actually have the ECU on a test bench and we can supply and get power out of it. And by supplying power, as previously discussed with the ECU reset, we basically start the device again. We start from the boot process and we switch to the application layer. And as we discussed previously with the tester present, we are staying in the bootloader process. But what if we don't have a way to physically perform this, to physically perform a power cycle and we're in a full vehicle pen test? Do you remember this guy? So here we have the same principle. Instead of controlling the power source of the test bench, we control the battery isolator, which is publicly accessible, as we saw, and isolates the power source when the switch is off, and supplies power when the switch is on, technically allowing us to bypass programming session and ECU reset restrictions from the application layer and by supplying this tester present, we can also stay in the boot process like we did before. yeah, here is a summary of what was explained. Basically, the ECUs are mainly powered by the internal 12-volt battery. So in EVs, this is also applicable from the AC inverter, which is supplied by the vehicle batteries. So isolating the power source technically turns off the ECU, and by supplying power again, we initiate the boot process and everything that comes after that. But what about the hidden bypasses? And now I want to mention the UDS fuzzing and the path to game over from last year, where we basically bypassed the security access mechanism because of seed randomness, which was based on the system clock and all vulnerabilities that are becoming new again. This is something that we were discussing 20 or 30 years ago. Manufacturers start realizing this and mitigating it eventually, and this is like an especially big issue for the tier ones and the OEMs, but did they actually realize? So here we have another example. We have the normal boot process, and when we are on the application layer, we have the security access service available, 27, and let's assume that we have the sub-service 03, which its purpose is the execution of restricted routines, so like execution of some kind of authenticated service. And let's assume that the seed source of randomness is the HSM, which is considered secure, it's considered okay to use, we have a really good entropy. But by hard resetting of any kind that we saw before, we find out that there are several different sub-services and services. In this case, we have, again, security access for authentication, 27, and we have a sub-service which is 01. So it's different from the one available on the application layer. And the purpose of this sub-service is reprogramming most of the times, because it's on the boot section. And the seed source of randomness, system clock again. I don't understand why. And some of the things, several reasons that we can think of, maybe it's forgotten, like that can be a reason, or there are separate development teams handling the bootloader and application, or even externally sourced. So there is a completely different code base in this case. As discussed, even if everything is protected under the bootloader, access to it can probably be obtained and services can be accessed. It worth testing all available services and sub-services, even if the assurance that we have the assurance that they are the same by the OEM, cybersecurity requirements, or even the tier one. And the story of duplicates once again, but with a twist. Basically, last year we developed a module, the seed randomness fuzzer for Karin Caribou. Karin Caribou is mostly a modular tool for automotive security. The main advantage is that it's easy to use and easy for people to start with and understand how to enumerate UDS and other protocols in the automotive. And yeah, there is the case that many people don't like it because it's so high level and you cannot actually change the lower levels of the communication, but usually we use it for some easy checks and quick checks. So let's go to our final use case, and we are targeting a hydrogen ATV, which for safety critical reasons need to be easily isolated from the batteries. After enumerating, we discovered that ECU reset is not available in any diagnostic session. The available security access is not backdoor, all vulnerable to weak seed randomness, and no other misconfigurations discovered during the initial enumeration. So basically, we are locked in the application layer, and we cannot do anything about it. And here comes some more automation. We have basically the battery isolator and some Raspberry Pi with some relays, or any relays that you can use connected to Linux or to the tool, whatever platform you're using. And we will get similar results as last year, where we managed to receive the same seed more than once, as you see. On the left side, you can see that basically we request the seed, and every time we receive the same. And in this case, we bypassed several layers of programmatic protections by exploiting design and architectural choices made by the OEM, because we are using, instead of using all the authenticated ways that were restricted, we use the battery isolator and the relay connected externally to the vehicle, to the fuel cell ATV, in order to reset the whole vehicle and get access to the boot process, which sub-service was vulnerable. Yeah, in our example, having a relay as a source of power cycle basically results in even more accurate results from last year, with around 20% of duplicates out of 1K samples. We can be relatively confident that the target is sourcing the randomness on the system clock. Additionally, in most cases, it's easier to maliciously intercept a seed and pre-calculated key from the bootloader accessible subsession than from the application layer one, as it's used for reprogramming purposes, and it might be used more often than the application layer ones, either by head unit managing an update or by service department updating actually the ECU. And let's wrap up slowly. While CC, like Karin Caribou, might not be the best tool out there, it can help newcomers start, and it's for sure a project which also helped us start. Several new automations were developed by my side to help the project move forward, including a right data by identifier fuzzer, another service that is applicable, an automated module for complete automation of the UDS enumeration that we previously saw, support for new CAN interfaces with proprietary drivers under Python CAN, and different padding and no padding support, which is used from some manufacturers. And as we reach the end, I would like to briefly mention the differences between performing a pen test and security research on the automotive industry, because it was also one of the goals. And while reversing firmwares and getting hardware access is fun, scope is usually extremely limited for the client in a pen test. For this reason, we are tasked to find efficient ways, like the one we presented today, to perform more testing in a result-driven environment. And automation of tasks is usually our main priority in these pen tests, with direct result the extension of our methodology and test cases, and sometimes the investment of our time in automotive research. And for the client side of the things, automotive clients need to understand our methodology and test cases, and we are the ones that need to properly explain it. Abstract results are not always a good way forward for the client, and education is the key to better collaboration with developers, as there is no clear standard methodology available online. In contrast to mature industries like web, infra, API, and other industries that this is applicable. And here is the serious finale and some food for thought that I wanted to give you before I close. My approach on the industry is a bit more romantic, I know. I care about making the world a safer place, and my way of achieving it is by doing my best to secure vehicles out there, by closely working with these manufacturers that we discussed, and by trying to spread this culture. And the thing is that most of them, especially the old ones, don't really care about this vision of mine, and try to undermine issues like the ones we discussed today. And of course, they don't care. Like, we live in a capitalistic world, like with greedy corporations, that the only thing they care is these financial incentives. So we have to survive. So for that, I want to say that the weight is on us, all of us, the pen testers, the hard hackers, the researchers, and everyone passionate about this field, to share the culture and make sure that these issues, like the ones that we considered, they are considered by the manufacturers not like modding ways, but that something like things that can directly affect the safety of the passengers and pedestrians on the streets. So thank you.
Hello, Thank you, Thomas, for the talk. Are there any questions? No questions? There's a question?
You were talking about the EU regulation in the beginning of the talk. Do you have did you have already some insight into the regulative text that will be published? And if so, do you have the feeling that it is helping at least a little bit to push the companies into the right direction?
Thank you. Actually, we were part of some of the certification processes in some of the OEMs. And the thing is that I want to stay positive. I want to say that it will help. And actually, there are some significant points that I believe that can help with certification and security in general for the automotive sector. But my message to that would be that this has to be done properly. And there are several layers into this process of certification, which is the certification authorities, the regulators. There are several layers that has to be maintained and has to be performed in a proper way. Yeah. So I cannot say if it will be done properly because it comes into action in 2024, but I hope for the best. Yeah. Thank you.
Any other questions? I don't think that's the case. Okay, thank you very much then.
Thank you.